Good morning, everyone. My name is Anand Mantri. I'm a senior principal with Kearney. We are a management consulting firm, and I do a lot of my work in the energy space. Very heartening to see the kind of conversations we are having on green hydrogen, which actually is the truly net zero fuel of the future. It will take some time, but glad that the entire ecosystem is talking about it. Today's technical session has a lot of interesting and relevant topics. We'll talk about storage solutions. We'll talk about predicting renewable prices, which is very interesting. We'll also talk about safety standards, which will be important as we deploy hydrogen on ground. And then more so producing hydrogen from new alternate sources rather than just the renewable source. So without further ado, I would want to invite our first speaker. We have a total of 5 speakers here. I'll want to invite the first speaker, Mr. Nawal Pande. He is a joint director, OISD, as a part of the technical directorate of MOPNG. He would want to present his insights on the safety standards for hydrogen. Sir, please, over to you.
Good morning, ladies and gentlemen. Welcome and thank you, all of you, for gathering. I stand before you with a message which is related to hopes and innovations with little bit of safety interventions in it. As we talk about this message revolves around safety, and it revolves around the very high potential of hydrogen as a future fuel to combat our journey towards hydrogen and climate change. In recent times, there is a lot of development in field of hydrogen related infrastructure, especially electrolyzer manufacturing, the materials, the detection systems. All these systems are in development, but the main question arises, what about the safety? Are we prepared to take the risk? Are we prepared to understand the risk? Whether this is a similar kind of a energy carrier like other hydrocarbon. So in order to understand, let me bring the perspective in. So why hydrogen is different from others? There are 3 attributes of hydrogen. Number 1, energy content. Number 2, its size. And number 3 is reactivity. Now, if you compare with its size, it's a very tiny size. So it basically provides the permeability. And again, the reactivity, it's a highly reactive molecule. As we know that the free radical hydrogen is not only responsible for all kind of reactions, but also responsible for our body reactions. So free radical mechanism is highly reactive mechanism, and that's why perhaps the God has started creating this whole Srishti with the help of hydrogen. If you look back 4.6 billion years ago, the first sunshine showered on our planet Earth. From there onwards, the journey of creation of life and creation of energy and its containment of energy has started. So we can say that hydrogen is the great granddaddy of energy. If hydrogen is at its core, so everything which is emanating from sun and making all form of energy on this planet is due to hydrogen. So why this particular molecule is responsible for all form of energy comes from these 3 facts. Its high energy content, its high permeability, and its reactivity. So purely from the energy business point of view, the high energy content definitely is very attractive. But from the safety perspective, its size and its reactivity, these are the 2 major important things which I will deal with. And I think this is a differentiating factor between normal hydrocarbon and hydrogen as an energy carrier. And initial accident, let me come to the part which most affect any business. That's the accident. Let me tell you this, that initial accident in this ecosystem going to be deal breakers. I have an example of Hindenburg that was a great deal breaker at the time when this accident took place in perhaps in 60s. Accident investigation revealed that the accident didn't took place because of hydrogen. The accident report says there was a cellulose nitrate paint on the airship only. The investigation report reveals that it was an orange flame. It was a gasoline fire. But eventually, hydrogen became the scapegoat of it. So the initial impression, the public perception went that hydrogen is very risky. In fact, few years back, the same kind of accident took place, and at that ship, in spite of hydrogen, there was helium. So you can very well understand the root cause analysis and the perception, public perception. These are two different things. So as we are developing this, our whole ecosystem, the accident investigations and accident happening at initial days will be very crucial. So we have to make sure, with the help of regulators, with the help of standard making bodies, and with the help of industry, with their pilot studies, that they meticulously design and provide adequate safety measures into their hydrogen systems. So understanding the hydrogen risk will be the first step towards the pathway of scaling up and utilization. Let me tell you that safety is color blind. As far as we talk about green hydrogen, various colors of hydrogen, but as far as safety goes, hydrogen doesn't have any color. We are not racist in that sense. Now, before I go into the technical details, let me tell you what kind of incident, there are several incidents took place in the past, from where we can learn. This is one of the Indian refinery where there was a catastrophic failure of hydrogen valve. That valve was particularly meant for handling the hydrogen. It was not a very high temperature facility, and the valve was replaced, and it was made in India. So when we investigated, we found that there was a problem in the inside welding of the valve. There was a material defect. The material which should have been there was not there. So within 42 hours, that valve catastrophically failed. Although there was no loss of life, but there was a loss of property and there was a production loss. So because of embrittlement effect, hydrogen can very quickly, depending upon circumstances, depending on the process parameter, can quickly create a havoc. So we have to be very careful while choosing the material and while changing the material. This is an incident which took place, and what happened that in a storage tank of hydrogen, oxygen got mixed. So the blast was so devastating. It was only 10 bar storage facility, and the blast was so devastating that in the vicinity of 100 meters, most of the structure got completely damaged. 2 people died in this accident. And perhaps this particular downstream thing was basically after the purification facility, when the hydrogen comes from electrolyzer. Perhaps there are no confirmed reports, but it is expected that some membrane fault was there. That's why the oxygen and hydrogen got mixed and got stored. And perhaps if you have a pure oxygen and pure hydrogen in a perfect combination, you hardly require any ignition source. I mean, hydrogen ignition energy is very low. Even corona discharge can ignite it. So such kind of, this is a new thing because electrolyzer, hydrogen production by electrolyzer, and then its purification and storage is going to come. A lot of facilities are coming. So we have to be very sure that we mix we do not mix hydrogen with oxygen, because pure oxygen takes away the upper flammability limit up to 95, 96%. This is a trailer filling station that in the facility it took place. There was multiple errors in this particular process. There was no lockout procedure followed, and the driver was not trained. In fact, driver was not responsible for taking the actions which he was taking. What happened that when the unloading activity up to 90% was completed, the driver found there is a leakage. So he started attending that leakage, although it was not his job. But with his accompanying a person who was not trained, he was under training. He asked him to isolate the valve, but unfortunately he opened it. So there was a major leakage and explosion, although no one died. But these are the incidents which will tell you that not only the technical failures, but also the human failures, the non-following the procedures, is also responsible for such kind of accidents. Now, coming to the properties of hydrogen which contribute the higher risk, the combustion properties, and as we know, flammability limit, everybody knows that hydrogen flammability limit is from 4 to 74. But this is not precisely true, because these properties are not the universal properties like atomic mass, density, and these are the properties which are depending upon temperature, pressure, and the environment around it. How much level of confinement is there? All these factors will decide the flammability limit. For example, the flammability limit, if the leakage is from horizontal direction, is different, and the flammability limit when it leaks in a downward direction is different. Ignition energies, hydrogen has a very low ignition energy. It is only 0.019 millijoules. So almost negligible amount of energy is required to ignite the mixture. In fact, in most of the cases, the ignition source could not be ascertained, because it takes nothing and it takes no reason to ignite. Again, flame propagation of speed of hydrogen is very, very high. That's why, because of this high propagation speed, the deflagration in an explosion phenomena, the deflagration converts into detonation very quickly. In most of the cases, if the deflagration is there and there is a confined space, and then there is a large possibility that it will result into detonation. The flammability, the properties which will have a effect, that is, it's a thermal effect, the pressure effect, the easy ignitability. This is the flammability. It contributes a higher risk than any other hydrocarbon. A small size of molecule, low viscosity. People say that low viscosity is good because it actually helps in dispersing. There are other related phenomena like high diffusivity, low viscosity. But ultimately, if you have a low viscosity, then in a fixed size of hole, you have a more flow. So if a natural gas leaks from a 1 by 8 inch, the leakage rate in case of hydrogen is pretty more. In fact, the leakage velocity at a certain pressure will also be very, very high. So it reaches to sonic velocity. Interaction with material, this is something, a new phenomena which happens with the hydrogen, especially for the high strength materials. Embrittlement, hydrogen attack. Hydrogen attack is visible in refineries where we handle high temperature. There is a difference between hydrogen attack and embrittlement. In case of hydrogen attack, the hydrogen goes into it and forms bond with carbon and becomes methane. So the ductility of the material catastrophically can reduce and can fail the material. The hazard associated with the storage, the elevated pressure of the gas. In fact, if you talk about energy content of hydrogen, we must definitely go for higher pressures in order to match the energy density with CNG. For example, if in CNG you require 250 bar of the pressure of the cylinder, then here you have to go up to 700 bar at least in order to match that the mileage required necessary to make it commercially viable. So elevated pressure will result into very high leak rates, will result into uh, Mach, Mach level discharge, means a very high velocity discharge, which may result into explosion phenomena. Normally people say that hydrogen has a very, because of the buoyancy, it will go upward. But in case of very high speed leakages, the high diffusivity results into very quick forming of mixtures, explosive mixtures. So in fact, that phenomena goes negative. Some people have a myth that hydrogen, since very light, it will go up. But it doesn't happen in case, it happens in case of low pressure leak. But in case of high pressure leak, this phenomena goes against. Because of the very high turbulent zone, the mixing takes place very quickly, and hydrogen decay rate, the diffusion decay rate is pretty slow in comparison to other, for example, if you compare with natural gas. Its decay rate is pretty high. Means if the hydrogen leaks at a very high speed, it will remain there in comparison to methane for a longer period of time. So if longer period of time the diffusion is there, then definitely more chances of explosion.
Sorry to interrupt, Mr. Pandit. Time is up.
Time is
just,
up.
Time is up. Just one last minute to summarize, please.
Well, I'm at the middle of the presentation, so risk mitigation will change based on different kind of hazard identification. For example, if we have a more risk of explosion, then the pressure relieving devices should be differently designed. For example, rather than having a pressure, you have to detect the LEL rather than going for a pressure, because in case of detonation, the pressure relieving device will not work. Detectors, you have to have a specific type of detectors which is used for hydrogen. All catch type of detectors like Pallister type detectors won't work. You need a specific detector for hydrogen. Do not go for LEL detectors or simple hydrocarbon. Fire detection, because mostly the absence of impurity, hydrogen flame is almost invisible. So we have to critically examine the type of IR detector, because sunlight also have that IR, so there can be a risk of interference. So I have to, electrical considerations very important. It's a 2C gas, so you have to be, explosion proof equipment should be used in all locations. Lightning protection should be used. Hydrogen equipment should be electrically bonded, especially across the joints, with polymer seals and grounded. Mobile hydrogen equipment should be electrically grounded prior to be connected to the hydrogen equipment. Minimize the quantity of hydrogen. We have to minimize the quantity. There are regulations which are coming up. They will try to restrict the amount of quantity of hydrogen. Now the new type of risk assessment as prescribed by the NFPA 2, they say that the risk-based distancing, the risk-based identification of hazard is to be done. Initially, the distances was calculated based on the volume. Now they say that there should be a different pressure range, and there should be the diameter of the pipe, not the leak size. So there is a whole paradigm change in the way we look at the hydrogen safety. So minimize the personal exposure by limiting the number of people exposed, time that personal, elevate hydrogen system and vent above the facilities. There is a standard called CGA 5.5. All the hydrogen venting should be designed as per 5.5. It is an exhaustive standard on hydrogen venting and disposal. So it is recommended that we should go for this such kind of standard. OISD is doing its own bit on hydrogen. We are making standard on hydrogen safety. The standard will cover the minimum requirements for safety in design, layout of facility, construction material, equipment assembly, testing, commissioning, operation, and maintenance of hydrogen production, storage of gaseous liquid hydrogen in stationary containers, monitoring and control devices during storage, road transport, and pure hydrogen into pipeline blends through existing natural gas pipeline for transmission, and distribution pipelines for domestic and industrial use. The standard will also cover the risk analysis, hazardous area classification, and firefighting and PPE equipment. The path forward is we have to make the robust regulatory standard. In fact, the regulatory bodies like PESO and PNGRB are already they are working. They have already proposed the draft. So the standard is regulatory mechanism framework is coming in a very big way. Risk assessment is very important because very less data is available for hydrogen. So we need to generate our own data. For example, in case of a blended hydrogen, you have to do the pilot studies, training and education, public awareness, and collaboration. It's very important we collaborate with each other and exchange the knowledge. Hydrogen Tool is a website, very good website, which will give you a lot of information. So this is the path forward. I think I'm short of presentation.
Yes. So apologies for this, but I think
so. This is the last slide because I would, before any question answer, I would like to tell you that there is always a dilemma when it comes to business profit and risk taking. So a very good verse from Karma Yoga says that Shreya Swandharmo Viguna Param Dhanu Nudishta Swadharme Nidhanam Shreya Param Dharmo Bhayavaha. इसका मतलब ये है, मैं हिंदी में बोलूं, कि अपना जो धर्म है यानी सेफ्टी, हेल्थ और एनवायरनमेंट, ये हम सबका बेसिक धर्म है. कोई भी आप बिजनेस करें, उस धर्म को पालन करना श्रेष्ठ है. बल्कि इस बात को फॉलो करना कि इफ द बिजनेस रिक्वायर्स मोर रिस्क, फर्स्ट यू टेक केयर ऑफ सेफ्टी, हेल्थ एंड एनवायरनमेंट, एंड देन यू टेक केयर ऑफ योर ड्यूटीज. सो गीता गिव्स द प्रिस्क्रिप्शन ऑफ अ सेफ्टी प्रोफेशनल. With that words, I would like to finish my presentation, and if any question answers you have, I think last session can be taken. Thank you.
Thank you. Thank you so much, Mr. Pande. We'll take Q&A towards the end if we have time. Next, I would like to invite Dr. Sanjukta Subudhi. She's a senior fellow at TERI, and she will be talking about production of biohydrogen from biomass, which is again an interesting concept. Over to you, Dr. Sanjukta.
Very good morning to all. Hope I'm audible. Thank you very much to the organizing committee for providing this platform to speak on this, the core subject on hydrogen, green hydrogen. This presentation will be focusing on a different aspect, that is production of hydrogen from alternative resources. Those are based on the carbohydrate or the organic fractions. So I will be focusing on the lead that we have achieved at TERI with respect to the production of this clean hydrogen from broad spectrum substrates, basically those substrates which are rich in organic or the carbohydrate fractions. Before focusing on those data, I would like to highlight or briefly introduce about the pathway through which hydrogen can be produced biologically. Well, I will, in the interest of time, I will speak the introduction slide. Hydrogen can be produced from broad spectrum feed by using different type of select microorganism, because the way we use the catalyst to produce hydrogen from water through the electrolysis route, here we use the select microorganism as the host or the factory to produce hydrogen. And in these microbes, the select enzymes, they act as a biocatalyst to produce the hydrogen. So when I say the biocatalyst, then it is very essential to identify which type of organism should be used based on the type or the composition of the input raw material. So there are basically 4 pathways. One is the dark fermentation pathway. In this pathway, normally the organisms produce hydrogen in the absence of oxygen. We call it dark because this does not require any input light as an energy source. Coming to the second pathway, that is the photofermentation. This also occurs in the absence of oxygen, but light serves as an energy source. So we call it photofermentation. Here we can use the short chain volatile organic acids as a feed for production of hydrogen. Coming to the third is the photosynthetic process. This is exactly the way like we get hydrogen from water through the electrolysis route. It is photoelectrolysis process where the algae and cyanobacteria, they electrolyze the water and convert to the hydrogen. Again for this, and there is a integration. The integration is possible because of the type of input material that can be utilized by this microbe as we can see from the dark and photo fermentations. So one can decompose the organic carbohydrate fractions in the dark fermentation, and the intermediate metabolite can serve as a very good feed for hydrogen production for the photosynthetic process. Well, before starting any process, it is very essential for us to set the benchmark. What is the input material we are taking and how much energy in the form of hydrogen we can recover. In the dark fermentation is very extensively explored globally because the rate of production is very high through this route. And an array of broad spectrum feed can be used as the input material. When I say an array, then it is any spent slurry from the sugar industries, starch processing industries, food processing industries, biomass. Having said that, second and third generation biomass can be used as a feed. So if you see the calculation, 1 mole of glucose can produce 4 mole of hydrogen. And if we integrate that by using this metabolite for the photofermentation process, we can produce 12 mole of hydrogen. If I calculate 1 kg of sugar can produce 24 kg of hydrogen because 1 mole of hydrogen is 2 gram. So 180 kg of sugar can produce 24 kg of hydrogen. Well, so I will be focusing on the pathway or the lead that we have achieved at TERI for the dark fermentation. In the dark fermentation, we have set the benchmark. If I get 4 mole of hydrogen from 1 mole of glucose, then the process is actually efficient, which is 100% yield efficiency you can consider. If you see, so and when I say the right top of micro, when I choose any starch processing to starch-based feed, then the microbes should be able to utilize starch as an input material. That means the microbes should be having some enzyme that should degrade starch to the simpler fractions that can be amenable for the fermentation for hydrogen. If we are targeting to use biomass, biomass contains around 65 to 70% of carbohydrate, which is a mixture of hemicellulose and cellulose. The tricky part over here is that most of the microbes, they will feed on the hexose sugar, but a very few microbes, they will feed on the pentose. If I see for the cost economics, the microbes should be able to utilize both the pentose and hexose fractions. So we have used input material, all type of second generation feed like aquatic, the water hyacinth, azolla, and then the lignocellulose biomass, including the spent slurry from the ethanol processing plant, including the pentose-rich pre-hydrolysate stream that we get after the biomass hydrolysis, which is the pre-treatment step for going even for the 2G ethanol production. So here we have selectively isolated and domesticated a very good microbe that could feed on both pentose and hexose. Then what is the benchmark? The benchmark that the microbes should be able to produce at least 75 to 80% of hydrogen yield efficiency from that input feed. And the second is the process time. For the biological process, it is cost effective because we consider the one is the cost of the input feed, second is the bioprocess cost. The bioprocess cost is directly linked with the process timing. So we normally look at for reduction of the HRT, hydrolytic reduction time. So this microbe could utilize this pentose and hexose feed to produce hydrogen, and the process time, the HRT could be around 15 hours. So when I say 15 hours, well, this is the pathway that the microbe is following up. For hydrogen, apart from the hydrogen production, this microbe also release some of the intermediate metabolite, that is acetic acid and some fraction of ethanol. And reaction stoichiometry says that if we are getting acetic acid as the metabolite, then we can produce or maximize the hydrogen yield recovery. And second thing is that you optimize the parameter in such a way that the most of the input raw materials should be diverted towards the hydrogen. Hydrogen actually is a byproduct for the cell. After production, this hydrogen comes out of the cell. So after optimizing all those parameters and observing that this microbe is a very good microbe for implementing as a self-active for hydrogen production from biomass, we have gradually upscaled this process The left part, the bottle shows the pentose rich, the xylose and arabinose rich hydrolysate that we get from biomass hydrolysis pretreatment step. So, apart from this yield efficiency or the substrate utilization efficiency, this microbe is very robust that it could tolerate the furfural and HMF which is present in the hydrolysate and could utilize the hydrogen production. Gradually, you have upscaled up to 30-liter scale because of the thumb rule in biologically when you try to validate any process, one must validate the result at a 10-fold higher scale. So, then we have gradually upscaled this 100-liter scale. Now for the volumetric conversion, I would like to highlight over here. In the fermentation process, we normally use a water-based broth fortified with the input, the carbohydrate-based component. Within 15 hours, this microbe could generate around 2.5-fold higher volume of pure hydrogen. When I say if our hydrogen fermentation broth is 100-liter scale, then we got around 220 to 250 liter pure hydrogen. Rest is around the composition, biogas composition, it contained around 40 to 45% CO2. After scrubbing, we got ultra pure 99.999% pure hydrogen. And we also got some acetic acid as the metabolite. So going forward, what we did that we have then tried to utilize all type of biomass. When I say the rice straw, wheat straw, sugarcane bagasse, sugarcane truss, sorghum stubber, and then the water hyacinth, acornia, whatever the biomass, whatever the fraction that contains the carbohydrate-based feed. And the good part is that this microbe is very, very robust. It could feed on different type of carbohydrates so that it could utilize the pentose, hexose, simultaneously, and also the maltose and area of carbohydrate which are present in these all type of microbes. Because this process is anaerobic, the process has to be conducted strictly under anaerobic condition. So that is another aspect which is a cost reduction of this process. For any fermentation, if you see, if the microbe is the aerobic, you invest lot more energy to optimize the air and the air providing the air flow. Anaerobic, you don't need to anything. Just before kickstarting this process, create an anaerobic condition in this bioreactor. Having said that, you just remove all the oxygen by purging with some inert gas, which we have used for using a nitrogen generator that could generate 99.999% pure nitrogen. That nitrogen initially purged before inoculating our cultures, and then we did not purge any air, any nitrogen, anything else into that system. So the system just, we provided agitation at a minimum rate just to keep the cells circulate in the system. So as you can see that this microbe it is a monoculture based, and by optimizing these parameters, we could reduce the hydraulic retention time to 15 hours. So now coming to the cost part, when you have treated this biomass, if you see around 20 to 25% is lignin, and we have recovered that lignin and silica, and lignin is a very good feed, and one must look into the offsetting the cost of hydrogen that I'm getting, because the input energy is the biomass. I must look at into the fact that I'm recovering all part of this input raw material composition in the form of some product, so that I can offset the cost of hydrogen by co-producing some high-value product. The lignin part we are using as a feed from high-value biochemicals, again through the fermentation route, and the metabolites that we are getting, that is acetic acid, we have integrated that with integrated membrane-based technology and recover that acetic acid. Now, this acetic acid can be used as a high-value biochemical for the industrial application, so that one can offset the cost of this both acetic acid and this hydrogen, as well as the lignin-based product. Otherwise, this acetic acid is a very good feed for the biomethane production. So I will highlight in the end why there is a great potential to link with the biogas or the biogas process. Going forward, we have also worked on use of the third generation biomass as a feed for the biohydrogen production. When I say the third generation biomass is the marine algae we have focused, we have developed a process and demonstrated at 1,100,000 liter scale. It's a special sunlight distributed system that is being established in Mumbai coast aeroli. This system is producing marine alga using the sea water and the atmospheric light. And this marine alga, after we have developed this integrated technologies for on-site harvesting, and this after lipid extraction, which is around 20%, this de-oiled alga contains 30% of carbohydrate. So that carbohydrate also we have used as a feed for biohydrogen production. This slide just shows why it is very much essential to look at development of technology for biofuel in integration mode with the biochemical or biocommodity production, so that one can offset the cost of biofuel with the biochemical. So we have developed these technologies under different vertical by using this algae biomass as a platform feed. Since this is on hydrogen, I will not be focusing more on this slide in the interest of time, but I'm happy to take some queries. Now, the de-oiled algae biomass, which contains around 30% of carbohydrate, those are mostly the starch-based feed. Now, we must look at for using some microbes that have potential to utilize starch as an input raw material or the feed for the hydrogen production. Again, we have followed the same approach to identify right type of microbe. When I say the right, what is the benchmark and how much yield I am getting compared to the 100% benchmark. So again, we have selected a very good consortium of Clostridium cultures, and as you can see that we could get around 75 to 80% of yield efficiency. So these microbes we have used as a feed for biohydrogen production from algae biomass. Why I am showing here? Because whenever we interact with any of the industry, before commissioning any plant, the major query for them is the input raw material sustainability. So we should select some microbe that should be focused, that should be capable of using multi-spectrum feed utilization potential, so that whatever the feed is available, one can consider either using the mixed feed or so that the plant will continue running. And yeah, just 1 minute. Like I mentioned, similarly, we have demonstrated for third generation biohydrogen at pilot scale. And this is one process we have already demonstrated at TRL scale with the funding support from Center for High Technology MOPNG in collaboration with HPCL. There we have developed the technology for hydrogen production from blackstrap molasses. This has been demonstrated in TRL 6 to 7. When I say that TRL 6 to 7 means 1000 liter working volume with a 1 cubic meter working volume. So within 18 hours, we could generate around 2.5-fold higher pure hydrogen, and that is 99.9% pure. The co-product that we got is the organic acids. These organic acids we have used as a feed for biogas production. So we have also developed a process for high rate biomethane production using this gas. So there is a great potential to link this process with the biogas process, because in the same biogas reactor, we have the different type of microbe. Even if the hydrogen is generated, the methane producing microbe, they will consume hydrogen. So if you can link that process with the hydrogen production in the first step, we are recovering hydrogen in the form of energy. In the second step, we are reducing the process timing, and we are generating ready-made the acid-based feed for the methane. And one can definitely think of mixing hydrogen with the methane, so the biohythane, which is a very high calorific value. So we gratefully acknowledge the funding support that we got from Ministry of Petroleum and Natural Gas under the CST, and then from Department of Biotechnology, we got the funding for all first, second, and third generation biohydrogen production process that we got from Ministry of Science and Technology and all that team. Thank you very much.
Thank you, Dr. Sanjukta. And if this scales up, some PEVC investors in the house you might be hearing and you might be interested. With that, we'll invite our next speaker, Dr. Sachin Chugh. He's a part of the R&D team at Indian Oil. And Indian Oil, as we are aware, operating refineries, hydrogen would be the application which reaches refineries as the first off-taker. So he would be talking about hybridization technologies on green and blue hydrogen. Over to you, sir.
Thank you to the organizers and the session chairs for giving me this opportunity. And I'll try to stick my talk within the allocated time of 14 to 50 minutes. To begin with, I would state that in the intricate tapestry of energy, the interplay of electricity and hydrogen, obviously produced from renewable energy, it emerges as a poetic combination. It emerges as a coherence of electrons and molecules, and together they weave a panorama, a narrative, where the elegant choreography of electrons and the poetic symphony of hydrogen molecules is going to change ways in which the refineries are going to work. And this metamorphosis of the refineries is very much essential in the energy transition era. Now, my talk of today, hybridizing strategy for green and blue hydrogen production in the refineries, it actually covers the marriage of the green colored emerald stone, those dreams, and combining them with the blue azure aspirations of how the refineries are going to take forward and present themselves as the sustainable source of energy for the future. There is a challenge in which we have been asked to decarbonize. Two ways we can look at it. We can reduce the global carbon intensity. The vertical downlines, which we can afford to bring, only is possible when we emit the carbon from the molecules. And there is energy which is used as a primary conversion, and the prime movers have to have higher efficiencies when we go forward as far as the mobility sector is concerned. But I would try to concentrate on how, if we have to reduce the carbon from the molecules, there is a lot of development which is happening in India. Refineries are at the forefront of it, but we are trying to replace the natural gas molecule with the green hydrogen. Now, whether this is the right thing to do, or we should aim at replacing the more dirtier molecules like coal sitting in the power plants, or maybe the diesel sitting in the fuel tanks of the vehicles. But as far as refineries are concerned, we have been producing hydrogen from natural gas, and this is how we are going to replace with the green hydrogen. Now, when we start implementing and conceiving those concepts, there are various challenges and various trade-offs which can emerge, and we need to address those things, particularly when we are talking of implementing the projects at a very large scales. It is whether the moving of electron or the storage of the electron, which pathway to choose. Generating the electron or producing the molecule, how the interplay can happen and how the optimization can be done. Creating the asset or the new asset in the form of electrolyzers versus utilizing the existing ones in the form of the reformers which we have already set up in the refineries. Those is going to play very heavily as far as the costing is concerned. And so these are, and primarily there is a standard of green hydrogen which we all need to qualify as a country, and this is how we have to base our strategies. So this particular analysis which I'm going to present is basically addressing how the electrolyzer operation changes vis-a-vis the renewable energy capacities which are going to be implemented, how hydrogen storage volumes are going to vary with the continuous power availability, how the renewable energy capacity additions, it addresses or it behaves vis-a-vis redundant utilization of electrolyzers, and so on and so forth. So we did, we all have been looking at various electrolyzer technologies. These have been discussed in detail on this forum. I'll not go into the details of the technological metrics, but while we are choosing the technology for the refineries, or we have to integrate it with some other application like mobility, there are certain criteria which we need to address. The downstream application, whether it is only for the process, or it is single, or it is hybrid, means are we going to link other applications of hydrogen from the refineries? I'm primarily talking for the industrial applications of green hydrogen as well as the mobility sector demand. What is the quality which is going to come from? So the choice of the above 4 technologies is also going to vary depending upon what is the process quality requirements. how we are going to behave on the turn down, what is the degradation of the overall stack life or the cell life over a period of time. The temperature and the heat balance is particularly very important from the process industry point of view, and how large are the footprints, combined footprints, the electrolyzers as well as the RE plant when we talk of the microgrids. This is the snapshot of the Journal Refinery. We do have the hydrogen generation units, which are primarily based on the natural gas. We do have hydrogen coming up from the continuous catalytic reforming, which is primarily the in situ process used for converting naphtha into the high octane gasoline. And this particular volume has to be taken into account because we can't offload these things and replace them with green hydrogen. So there is an asset on ground in the form of hydrogen generation units. There is a natural hydrogen availability in the refinery or getting generated in the process in the form of CCR. And now over and above that, we want to have the green hydrogen. So how these things are going to balance is the thing which we have to see. So we studied 4 cases. The electrolyzers getting installed in the refinery. However, they are supplemented by a lot of the hybrid infrastructure in terms of the solar and the wind, which is the way to go about it, rather than going solo either on solar or wind. And then these electrolyzers getting to the refinery balanced by the CCR, and we are augmenting it by the green hydrogen storage that constitutes our case number 1. The case number 2, we start operating the existing assets in the form of hydrogen generation units. Don't want to waste it. A lot of capital investment has already happened in the refineries. And so thereby we can reduce the capacities of the electrolyzers to be installed in the refineries. Hence, we can do away a little bit on the power consumption side on the upstream, and balance it with the hydrogen generation units and the hydrogen coming from the CCR. The third case is primarily how to utilize the electrolyzers for 24/7. We may not be able to have the higher availability of the renewable energy 24/7, and therefore can we fall back on grey power for a time being till the situation is set all right for the green power, and then we can actually reduce the cost or the capital cost of electrolyzer being informed. And then fourth one is how we can do it with integrating it by the carbon capture technologies and reduce the overall carbon footprint. So what we found was that the case number 1, which is a case with keep the hydrogen from the CCR to maximum, and hydrogen generation units, both stopped. So there is going to be the loss of the capital investment for us, and then maximizing the green hydrogen. So this overall results in the capacity. The refineries can achieve about the green hydrogen capacities of about 70% or so, thereby leading to the transition which each one of us is looking at. But this does require a lot of upstream augmentation in terms of the infrastructure to be set up on the renewable side, both solar and wind, as well as a lot of electrolyzer capacity to be added within the refinery ambit. And mind you, the cost is going to be extremely high. So whether this case is favorable or not, I'll just discuss in the upcoming slides. The case 2 is we start using the HGUs primarily to take care of the night requirements. However, during the day also they are operating, and reduce the electrolyzer capacity to about half. Therefore, the upstream side of the renewable energy can also reduce by more or less by half, and continue to operate the hydrogen generation units, maybe on natural gas, maybe on biogas. That's a different subject. But this way we can utilize our assets, and therefore the kind of cost numbers which we are looking on, they can be decreased substantially. But here we will only be able to achieve about 33% of green hydrogen requirements for the refinery, and the rest 67 will be coming from the conventional like it is coming now. The case 3 is primarily bringing in the grey power into picture, and going ahead with the similar kind of electrolyzer capacities of about 267. So this is a typical refinery case, but augmenting this or supplementing this with with the equivalent amount of solar and the wind capacities, little bit higher considering the transmission losses and all. But supplementing the gray power is definitely going to increase the carbon footprint of the overall process. But here we are meeting about 40% demand both at the daytime and the nighttime by operating the existing hydrogen generation unit already installed in the refineries, and therefore we can have the three combinations going. One is the CCR, which is going to give me the hydrogen in situ hydrogen, the hydrogen generation unit, the existing ones which are already available, and then adding on the electrolyzer capacities. But this does here in this case we do not require any kind of hydrogen storage, which becomes very important from the cost perspective as well as from the volume or the space perspective. The case number 4 is primarily the integration of the carbon capture technologies. The utilization is going to be a challenge in this, but yes, we want to keep the hydrogen from the CCR to maximum. We want to balance the remaining hydrogen with the HG1, which is going to be on a hot standby without hydrogen storage again, but with the integration of gray power combining with carbon capture technology. This way we can actually increase the hydrogen availability from the conventional ones, which we term as the blue one, to about 67%, and the green hydrogen would be about 33%. It can be increased to 54% when we start using gray power and start using the electrolyzer through continuously for 24/7 operation. So this way, these are the 4 different pathways which we studied, and if I present them in a nutshell, so we have the variables like what is the running load, what is the hydrogen storage capacity, and what is the electrolyzer capacities which are needed. So we found that the case, we can have the lowest possible electrolyzer capacities in case 2, and we can also reduce in case 3 and 4 also. So however, we can get rid of the hydrogen storage from case 3 and 4, which does use the grid electricity which is already available. And the moment we start greening the grid, the emissions which are shown in the last graph from these cases are going to further come down. So this basically comes out with how we can enhance the green hydrogen adoption, or overall per se the clean hydrogen adoption in the refineries as a optimal mix of the green and the blue. And we found that there are many other methods, many other optimization methods which are available, rather than only depending upon keep on adding the electrolyzer capacities in the refineries. Probably that is not going to solve the purpose for us, in a sense that it is going to be highly cost intensive. The availability of the electrolyzer technologies and the scale up has been discussed at this forum at length. So in order to avoid these things, probably in the next 5 to 7 years or 8 years, continue to use whatever we have at hand and keep on augmenting these capacities of the electrolyzers. That seems to be a better strategy. Finally, when we say and when we sum up, there are multiple parameters like how is the hybrid infrastructure capacity which is required, the electrolyzer capacities, the storage ones, the green and the blue combinations, then the CO2 emissions. Each case has its own merits and demerits, particularly the choice of the pattern is going to depend upon what is the priority for us, how the mandates are going to flow in, how much we will be allowed to pass it on to the consumers in terms of the escalated prices which are going to impact the gasoline and the diesel production in this particular case, and therefore this becomes a very cautious choice. Now, also, when we are looking at the refineries, it is not only the process units which we are going to focus upon. Particularly, the talks of the hydrogen hubs is in picture, and we can pose ourselves as one of the natural hubs, hydrogen hubs. Considering the fact that a lot of hydrogen is going to be available in the refineries, and these refineries can act as the support system or the support mechanism for powering the mobility applications. And in one of such endeavors, we have been doing an experiment on the hydrogen fuel cell mobility, and all of you must have seen the bus which has been showcased here. So this bus has actually passed on, and we are trying to assess the multiple aspects of the performance, and trying to see that how tomorrow refineries can support the mobility applications, particularly by having the refueling infrastructure right at the doorsteps of the refining of the refineries. So these are some of the exciting developments which are there. Just to summarize it, green hydrogen and refineries. This is a new emerging cocktail. It's a new relation, and therefore it needs new solutions and optimal solutions. Wedding with RE power is inevitable, but the approach has to be very cautious till the upstream sector improves. The cost and intermittency needs to be balanced. We have to have the twin combination of green plus blue, which actually would improve a lot of reliability, the primary factor on which the process industry like us depends upon. Cleaning of grid is going to have a significant impact, and it can have further lower down the emissions. And CO2 utilization after capturing does have a lot of constraints and need a lot of research, how we are going to overcome these constraints. So with this, I'll just try to end my talk, and thank you very much for your patience here.
Thank you, Dr. Sachin. This is fantastic analysis. We talked about configurations, how much renewable, how much electrolyzer, whether we should go for green or blue. Next, I would invite Mr. Yogesh Meher. He's from McDermott, and he'll talk about storage solutions, which is another important configuration as we go forward, balancing the entire act of upstream and downstream. Over to you, Yogesh.
Good morning, good afternoon. My name is Yogesh Meher, and I'm the Director of Engineering at McDermott. I specialize in low temperature cryogenic storage, and storage is becoming a very key component of today I'll be offering you storage solutions that are going to help meet the hydrogen demand. Obviously, hydrogen demand is going up everywhere. There is a need for decarbonization, and a lot of governments are now requiring a carbon-free footprint on your projects. Green hydrogen obviously is environmentally friendly, as everybody knows, and there are a lot of incentives all over the world that are basically focusing on a net zero energy systems. A lot of hydrogen demand is going up. It is becoming a good alternate for fossil fuels, and obviously the rise in demand for fuel cell electric vehicles all over the world is also adding to the hydrogen demand. I did present here some growing demand for hydrogen by the sector. A lot of it is going to be consumed by transportation by 2030. And on the right-hand side, you will see a key map of some of the projects that are ongoing all over the world as far as hydrogen in different infancy, from infancy all the way to operational. There's quite a bit of activity happening all over the world for that. For CB&I and McDermott, we have had a long and strong position in energy transition. Obviously, we have been in energy transition for the last 60 years, since 1956. We have built a lot of ammonia terminals, ammonia projects, ammonia tanks, and also a lot of hydrogen storage all over the world. Hydrogen generation infrastructure is going to be the key and a key aspect of your needs as a client. Obviously, if you look at the different colors of hydrogen, whether it's green, blue, gray, all of them lead to some sort of storage requirement. Ultimately, it results in either a land-based storage of hydrogen, a land-based storage of ammonia, or a transportation of hydrogen. That is something that is also being explored quite a bit right now. So how can hydrogen be stored? Obviously, you're producing it in a large amount, and how can that be stored now? The storage of hydrogen obviously can happen in a gaseous format using bullets. If you have a very small compressed gas requirement at your facility, then you can store it in a bullet format or a small tubular vessel with a 20 to 700 bar pressure at about ambient temperature. or you can store it in a cryogenic sphere in a liquid format. Now, why you store hydrogen in a liquid format? Obviously, because if you store hydrogen in a liquid format, you have an expansion ratio of 850 to 1 for the gas. Obviously, the storage of liquid hydrogen would require to be stored at a very low temperature of minus 250 degrees Celsius. Another common way you can store hydrogen, and we see a lot of that all over the world right now, is in the form of ammonia. And ammonia basically can be stored in a refrigerated format. It has a higher product density, but surprisingly, it stores more hydrogen density than hydrogen itself. And that is a good advantage of having ammonia as a storage for hydrogen. Obviously, hydrogen can also be stored in some subsurface solids, but that's very uncommon right now. So let's talk a little bit about hydrogen storage in a refrigerated ammonia format. Ammonia obviously is a promising hydrogen carrier. It has about 17% of hydrogen content in weight. It is obviously the most effective method today in transporting hydrogen molecules across the globe. Liquid ammonia is transported all over the world on a regular basis. Ammonia has a very high volumetric energy as far as hydrogen. So if you're trying to transport or store a large amount of hydrogen and you want to avoid a lot of energy losses, then ammonia is a very good solution for that particular storage or transportation option. And ammonia can be cracked or processed into hydrogen and nitrogen. You take the hydrogen and use it as a clean energy production, and the nitrogen is just released into the atmosphere. Some of the things that are on the right-hand side here, I would like to point out is the flammability of ammonia versus hydrogen. Hydrogen obviously is highly flammable compared to ammonia. Hazardous area rating for flammability is 4 for hydrogen and 1 for ammonia. But from a health hazard point of view, ammonia definitely is far worse than hydrogen. Refrigerated ammonia obviously can be stored in large tanks. We build these tanks on a regular basis. There are very definite codes in the United States and Europe, API 625, 620. So there's very prescribed method in which you can store ammonia in a very large amount. The material used is not very exotic. It's very readily available, low temperature carbon steel material. And the insulation options are there. You want to insulate these tanks because you want to avoid any kind of boil off of this ammonia. There are many different refrigerated ammonia storage containment options. These are all over the world. We have built hundreds of these. Obviously, a single containment, double containment, full containment. These options are there at your risk assessment, at the availability of the real estate, and obviously economics does play a big role in it. Here are different ammonia configurations. Again, a single containment ammonia tanks. These are mainly used by the ammonia producers and basically the ammonia industry as far as the farmers and the farming community. The double containment tanks are something that is more common now, and the scalability of those have gone up quite a bit. And the full containment tank is a best solution when you're trying to avoid and contain a large liquid leak of ammonia. Scalability of ammonia storage has gone up quite a bit. Out of all the tanks that we built in the past, we're looking at about 5,000 metric ton to 70,000 metric ton. And again, those came in different configurations and containment types, depending on the local regulations, risk assessment, economics, and real estate availability. As of today, we're building some of the largest ammonia tanks at 70,000 metric ton, which is about 102,000 cubic meters. We sit on a lot of these code committees all over the world, and we have basically have code changes all over the world now that are going to allow scalability of ammonia storage all the way up to 112,000 metric ton or about 163,000 cubic meters. Storing ammonia obviously doesn't come without risk. Safety obviously is a big thing. It is a dangerous and toxic product. A little as 1,700 parts per million of ammonia can be very fatal. Ammonia can cause some stress corrosion cracking. We all know that. It obviously rapidly reacts with a lot of metals as well. There are many factors that drive stress corrosion cracking, and there are a lot of driving factors for that, including some high residual stresses. Oxygen is a big factor for that. And we as an industry and with our experience have developed a lot of mitigations that we can put into these installations and into the storage that will help mitigate any stress corrosion cracking issues that are related to ammonia. Some of them are listed here. Obviously, the main thing is to reduce oxygen. Balancing the material properties is a big thing. Water is a very effective method for stress corrosion inhibitor. Obviously, a lot of ammonia facilities add 0.2% water. And obviously, minimizing the number of times you take the tank out of service. As far as pure hydrogen storage, what are the options out there right now? Obviously, gaseous bullets, gaseous hydrogen bullets are a good option if you have a very small volume that you're trying to store. Obviously, if you're trying to use something bigger in form of gaseous hydrogen storage, then your best option is to look at spheres. Liquid bullets, liquid hydrogen can be stored in small volume in bullets, but the scalability of hydrogen will go in liquid hydrogen spheres. And that is the best option that's available from a safety and as well as scalability point of view. So what is liquid hydrogen storage in a double wall sphere look like? Obviously, you have a double wall sphere, you have an inner tank, an inner vessel and an outer vessel, and you have some really good insulation material in form of glass bubbles. Different technologies are there right now. The codes that are used are ASME Section 8, Div 1, Div 2. The material for the inner vessel is obviously stainless steel. We use 304-304L. It's always impact tested at -320. 304 SS stainless steel material for low temperature hydrogen and at low pressure is not subject to any hydrogen embrittlement. So that is also a safety factor because you're storing hydrogen at a very low pressure, low temperature. The picture on the left is something that we have built recently for NASA. Again, scalability becomes a big issue here where you want to scale hydrogen to be able to store the volume that you're designed to store to meet the hydrogen demand. Why do you do that? Obviously, storing at a higher capacity allows you to achieve a reduction in land requirements, insulation, your overall cost goes down. You have decreased maintenance if you have a much bigger volume to store than many small volumes. And you're also minimizing the overall boil off of material itself. We started with hydrogen storage, liquid hydrogen storage back in 1960, and that was a small 175 cubic meter storage capacity. In 2022, we built the world's largest hydrogen storage sphere for NASA, and that was only 5,000 cubic meters. Since 2022, the demand has gone up, and we have increased those capacities all the way to 40,000 cubic meters. For a sphere that's about 45 meters in diameter. We are also scaling this up through additional studies with Department of Energy in the United States and some of the partners that we have in the industry. We are actually looking at scaling up liquid hydrogen storage all the way up to 100,000 cubic meters. We have the advantage being in the industry for 100+ years and obviously building these type of storages for 60 years or so. We can then scale up the land-based storage of hydrogen significantly and then apply that proven land-based storage to shipping. So we are working with a lot of shippers right now that take the land-based solution and then apply that solution to the shipping industry using those insulated spheres. We have a lot of patents on this technology. Obviously, when NASA approached us, they wanted to launch a Moon to Mars exploration program, and they found out that they did not have enough liquid hydrogen available in the system out there. So we built the largest hydrogen storage vessel for them. That is used for the Mars program now. And obviously, we have an innovative technology for insulating these hydrogen spheres because hydrogen is the particles are very small, it's very cold, and so we need to make sure that that insulation system that we come up with is going to basically achieve a low boil off and basically allow that liquid to be transported across the ocean. So as a summary, obviously I'm taking a little less time than you really appreciate that. The capacity limitations that you have today are not going to solve your problems for carbon-free aspirations for tomorrow. So you have to make sure that you have the capacities and the ability to increase those capacities should be there. Obviously, you have a lot of viable solutions in the market today for large-scale hydrogen economy. I showed you that ammonia provides one of the most effective methods for transporting hydrogen across the globe today. And ammonia basically has a lot of safety factors and features through different containment types and configurations. Obviously, you have to make sure you have the right appropriate material, welding procedures, testing for ammonia storage. And obviously, with the worldwide focus on hydrogen production, we want to make sure that we are able to meet the demand for storing gaseous and liquid forms of hydrogen across the entire globe. Scaling up safe hydrogen storage is available right now at 40,000 cubic meters. We are basically looking at scaling this to 100,000 cubic meters and obviously looking at making this available over large ships as well and shipping it across the globe. Thank you.
Thank you. Thanks a lot, Yogesh. Moving on to our last speaker. All of us are aware that renewable cost would be a significant 60 to 70% of the overall landed cost for hydrogen. We have Vishal Devgun from SLB, and he's going to talk about an interesting topic around predicting renewable prices for hydrogen production. Over to you, Vishal.
Hello everyone. First of all, thank you IEW and the speakers for giving us this opportunity to present our work. Today I'm with my co-author Karthik. He is a senior data scientist with over 15 years of experience, and this is our work which we have done in the industry. So today we'll be going to present a topic on forecasting electricity prices for
Vishal,
hydrogen production.
You could be closer to your mic, please. Thanks.
Is it okay now? Perfect. Thank you. So our work is on forecasting electricity prices for the hydrogen production using artificial intelligence. So we'll go through basic introduction first. I mean, in this session we have gone in length about the types of hydrogen, either gray, green or blue. So we'll just get us some few statistics. We'll see what exactly is the problem statement, and then we'll see what we have developed as a solution and how we can, use it as in the industry as of now. So from the introduction part, I'll start with some statistics from Government of India. So in Indian perspective, India has set a target to achieve a net zero emission by 2070. Energy use for India has almost doubled in last 20 years and is expected to grow by more 25% by 2030. And our export, we are mainly exporting almost 40% of its fossil fuel for our majority of components like petroleum refining, in fertilizers, and in mobility, you can say, in a nutshell. So this actually necessitates us to, reduce our dependency on fossil fuel and move towards the greener hydrogen, I would say, or more hydrogen production. So depending on the type of production, hydrogen can be defined as a green, gray or blue. I'll not go into the detail, but let's say if we are going with the hydrogen production through electrolysis. So one of the major component of running an electrolysis is the electricity required. So hydrogen produced by electrolysis has a huge electricity load requirement. So understanding the electricity prices is one of the key component of it. So is it possible if we are able to predict the electricity prices, because it depends on variety of factors. For example, what kind of weather in which we are producing, in which area we are producing, whether we are producing in a remote location or I would say in a city, then which day we are producing. So all these factors actually plays an important role in your electricity prices, because we are getting electricity from the grid. Now assume it, we are getting a green hydrogen, we are producing green hydrogen, we are getting from renewable resources. But one major factor, which is the electricity prices, which drives the electrolysis process over here. So we try to understand, what if we know the electricity prices for the next 24 hours? If we are able to forecast it, then how we can timely optimize our electrolysis operation, and we can place it in such a location which can help us to increase or improve our hydrogen production. So in this case, we started with the data analysis. We collected data from an open source, and we have data from four countries in the Europe. So the data consisted of different parameters like weather forecast. Since weather forecast is something which is available in the past, as well as we have the availability in the future as well. So in the past, we have the electricity prices and the load and the capacity fluctuations over time, the population and area of that particular region of the particular city. So considering all those data, we started with our exploratory data analysis. So this is our generic, I would say, machine learning algorithm, which we usually go by, starting with our exploratory data analysis to see clearing the outlier analysis or filtering out unnecessary data or integrating data, clubbing data, and then making filtering, joining, all those data wrangling processes we done. And then we add certain features also to it. For example, the holiday season. We know like Sunday is a holiday. So during that holiday, what would be the load demand? Whether that would be less or would be high. So all these kind of critical features which we have added, and then we developed different machine learning models. So basically they are deep learning models. So we started with basic moving averages. So we have taken two baselines. One is the moving average. We have taken basic 5 moving average is the first baseline. Second baseline which we have taken is the ARIMA model. This is auto-regressive integrated moving average. So, and the third one is basically about the TFT, the temporal fusion transformers. So we have run about 15 different models, but here I am showing like 6 or 7 top models which we have been dealing with. Talking about the ARIMA model, ARIMA is basically univariate, or only one single parameter is being taken into account, which is basically the time forecast. But in our analysis, we are dealing with such a data which has like multivariate. And we are not only dealing with multiple series, we are also dealing with past covariates and future covariates. Covariates are simple variables, we can say, and we have like past data available with us, and we have some future data also available with us. In the sense, we know what kind of season will be coming, what kind of vacations will be coming. So if we can integrate all those things into our model, then only it will help us to predict better. So we started with ARIMA. ARIMA is mainly for a univariate analysis, so we have to ignore it. Profit is by Facebook, now Meta. The problem with Profit is it doesn't take multivariate into account, so its accuracy is not that good. We started with deep learning models like deep auto regressions, LSTM. LSTM, the problem with LSTM comes with the learning methodology, the time dependency it takes very less amount of data in the past. So somehow, and it doesn't consider the future covariates also. So, and the last we take the TFT. TFT is basically temporal fusion transformer. Transformer is the basis of, I would say, it's a recently introduced deep learning methodology, which has many components like encoder, decoders, and then we have components like self-attention, like how much importance you give to the previous data and for how long you give that importance. So that is automatically be trained by machine learning itself. So the model automatically learns with the data, and with the future covariates available or the future data available, it helps us to predict. So this is how the temporal fusion transformer actually looks like. It takes into multiple data sources. So we have the historical data like price and the load. We have static data like your area and the population. Static in the sense is like it's not changing with respect to time over a long period of time. And we have a variable data also with us, like the holidays, season, the weathers, and because we have the weather forecast available for at least, let's say, next 5 days. So all those things are considered, and the workflow will able to identify for the next 24 hours in a some certain confidence interval, like in how much confidence I can say my price will remain in this region. So this is the final result of model training and validation. On the y-axis, we have the error, and on the x-axis, we have the number of iterations. With the TFT, we can actually see the number of iterations, our error are actually going down and up to a particular limit. So it helps us to identify a particular limit where we should stop. I'll not go into the bit detail of this part, but this is something which is very important, like the model explainability of TFT. The first parameter, which is the model attention means for how long the workflow is taking my past data into account. So here I can see like up to 25 days or 50 days, the workflow is taking all my parameters into account. So it is giving relevance, importance to my historical data and the historical patterns as well. Second is about the variable importance, like which variable are important to me, which variable I can ignore in this analysis, and which variables or which parameters. So these parameters can be my raw parameters, or it can be my critical features which we have created, either by filtering the data or by merging the data. And finally, the prediction intervals which I need to see. So I have explained this in a coming slide. So we started with the moving average. We can see the pink line is the predicted one, and the blue one is the actual one. So here you can see we can still see some kind of a error is there. But if we go with the ARIMA part, the first auto-regressive moving average, we can see we have a band also. In that confidence interval, we can see the price can move. So it is like your P50 is your middle line, which you could like an average, and P10 and P90 is on the either side, which is creating a band. And using the TFT, we can see that the band has merged, like the error has reduced drastically. So TFTs are one of the, I would say, a revolutionary steps nowadays. I mean, it is highly useful in our BERT kind of system or GPT kind of system. Although this is not a GPT level, but the idea here is to understand how my electricity price can fluctuate, and this will help me to understand where to put and when to on my electrolyzer operation on a very high level. So this is the final algo or a final summary basically. So we have done the study for 4 different cities: Denmark, Britain, Norway and Sweden. As you can see, the absolute error, I mean, we have simplified in terms of the absolute error. We can see that TFT has given the minimum error in this case, and the time taken to do all this processing is least in terms of TFT only. Whereas for other models, the time taken to model and validate is really high. And that is the power of transformers actually, which help us to, reduce the time and model quickly and train quickly. So in summary, as talked about by all the speakers, the importance of hydrogen. So I'll just focus mainly on the benefit of, or I would say the USP of this case. See, our data exploration has unveiled like we can estimate the optimum location where hydrogen prices are fluctuating. So the location where where electricity prices are less, where the demand is less, at that point we can optimize our locations. And by using the model prediction also, the stakeholders can time the operation of the electrolyzer to coincide with your period of low electricity prices. So it helps us to, thereby minimizing the production cost and improve the economic viability of this whole process. With this, I'll submit. Thank you.
Thank you. All the panelists' presentations were really very insightful. Quickly talk about the key points instead of kind of summarizing in detail. I will take Mr. Nawal Pande's point of view that I will take the last point of yours about the dharma from the Srimad Bhagavad Gita, what you talked about. That's very important. I think you talked about that dharma is safety. I will also add to your point that I think what you were also trying to say was that let perfection be not the enemy of good, so that we kind of move forward in the hydrogen economy area. So that's the point what I could gather. From Sanjukta, Dr. Sanjukta, I think biomass, using biomass for hydrogen production is something which you are looking at in terms of TRL 6 to 7 area now in terms of pilot production. Just one point, I don't know whether we can take this point that today government of India is also talking about biomass to be used for ethanol production. So does it conflict in terms of where the resources are going to get used? I mean, both ethanol and hydrogen both are alternative fuels, so it goes. So maybe that kind of point we can take it offline with the. From Sachin, I think Dr. Sachin, very nice talk from your side about hybridization strategies. You talked about CNG to hydrogen, and then you also talked about electrolyzer tech landscape. Three scenarios you have analyzed for hybrid architecture, but I think you talked about four. In the end, you talked about four scenarios as a summary. What I think on a lighter side, what I will just say is that you talked about hydrogen with refineries is coming out to be a cocktail. I'm not sure whether there is alcohol in it. If there is no alcohol, you can call it mocktails. From Mr. Meher, I think you talked about physical and chemical pathways to store hydrogen, and chemical is looking to be the best foot forward in terms of how do we scale up hydrogen storage. And I think ammonia is going to be a promising hydrogen carrier because of the fact that it can be stored at lesser temperature, minus 33 degrees Celsius compared to minus 254 degrees Celsius. So that is some area which we would like to explore going forward. From the last speaker, and not the least, Vishal Devgun, you talked about how AI can be kind of deployed for forecasting electricity prices for hydrogen production. I think that is something which is a new area. AI obviously is a new area. If we can deploy AI in the niche area of hydrogen, I think that can be a very good combination. You talked about the TFT comes out to be a best model, right? In terms of the 7 parameters what you had taken forward. I just hope that this is when this is applied, which has to be more than machine learning. How do you deploy AI in a real world solution, in a real world in terms of figuring out where's the sweet spot to take electricity for hydrogen production. This is something which I will request to you to look at. With this, I think I will conclude, and thanks again to all the speakers. Thanks to my co-chair Anand, and thanks to India Energy. Thank you very much. With this, we conclude the session.
Thank you. Thank you, everyone.